So if you throw like an apple core into the woods, nature just immediately gets to work turning it into nutrient-rich soil.
Right, it's a perfectly efficient system.
Yeah, but if you throw that exact same apple core into a modern landfill, it turns into this vicious greenhouse gas that actively accelerates climate change.
It literally fights back.
Exactly. And today, we are figuring out why human beings are the only species on Earth whose trash does that. So welcome to a very special deep dive.
And if you're listening to this right now, the odds are incredibly high that you have your AP Environmental Science Unit 8 test tomorrow.
Which means the clock is officially ticking. We need to, separate the signal from the noise. We are taking your class audio, your lecture notes, and study guides, and distilling them into one comprehensive review.
We aren't just going to rattle off terms. We're going to break down how these systems actually function, like at a chemical and biological level.
Consider this your ultimate audio study guide. And before we go a single step further, I need you to pull up Gage's Quizlet flashcards on your screen right now.
Seriously, keep that tab open.
Yeah, we are going to reference those specific terms throughout the deep dive. They're going to be your absolute lifeline on the exam. So let's start at the foundation. We create municipal solid waste, or MSW.
Which is just the everyday trash coming from houses and businesses.
Right. But I'm stuck on this whole idea of waste. Because in a natural ecosystem, the output of one organism is just the input for another, right? A tree drops a leaf, bacteria eat it. Why is our MSW so, fundamentally broken?
Well, it comes down to evolutionary familiarity. So fungi and bacteria have spent millions of years developing enzymes to break down organic stuff.
Like wood and leaves?
Exactly. But humans manufacture synthetic materials like polystyrene and complex plastics. Those have only existed for a century.
So nature just doesn't know what to do with them.
Right. We are synthesizing chemical structures that nature has no enzymatic key to unlock. They just sit there because the biosphere literally does not recognize them as food.
Wow, so we're flooding the system with these alien materials, and the volume is just terrifying. Like, Americans produce about 4 pounds of MSW per person per day.
Which is massive.
It is. But even when we try to choose the natural option, it gets weirdly complicated. Take the whole polystyrene versus paper cup debate.
Oh, that's a classic one.
Right, because paper comes from trees, so it decomposes. Sounds like the obvious winner. But making that paper requires, huge amounts of water, logging, and bleaching chemicals.
Yeah, the manufacturing side is brutal.
And then polystyrene, which is petroleum-based, lasts practically forever. But making it uses way less energy and water. It feels like a lose-lose situation.
It really highlights why you have to look at the entire lifespan of a product. And that brings us to life cycle analysis.
Oh, cradle to grave, right.
Exactly. You'll definitely see cradle to grave on the test. You can't just judge a product by what happens when you throw it away. You have to account for extracting the raw material.
It's a cradle.
Right. And then the energy for production, the use phase, and finally disposal, the grave.
Okay, let's apply that cradle to grave thing to something everyone has right now, a cell phone.
Good example.
So the cradle involves mining all these heavy metals, but when the phone eventually dies, the grave is usually just some random drawer, or it gets tossed in the trash, becoming e-waste.
Electronic waste. And that is packed with dangerous heavy metals like lead, mercury, and cadmium.
See, I struggle with this part. Lead and mercury are naturally occurring, right? We mine them out of the earth in the first place. So why is it a huge toxic disaster if they end up back in the ground in a landfill?
Well, it's all about concentration and biological availability.
Okay, what does that mean?
When those metals are locked deep inside ore deposits, they're isolated. But we dig them up, refine them into highly concentrated forms, and cram them into a phone.
Oh, I see.
Yeah, so when that phone degrades in a landfill, acidic water percolates through the trash and dissolves those concentrated metals. Then they leach right into the groundwater.
And once they're in the water, they get into us.
Exactly. They become biologically active. And heavy metals are uniquely awful because their atomic structure looks like essential nutrients.
Wait, really?
Yeah, like lead mimics calcium, so your body thinks,
Yeah,
oh, great, calcium, and absorbs the lead into your brain and bones. And once it's in there, it physically blocks your cellular receptors from working.
That is terrifying. Okay, test prep pause for everyone listening.
Yeah.
Make sure you have this written down. Check Gage's Quizlet right now. You absolutely need to know the 3 specific heavy metals in e-waste.
Lead, mercury, and cadmium. This will definitely be on the test.
Write those down. Lead, mercury, cadmium. Okay, so recognizing how dangerous this waste stream is leads us to the integrated waste management hierarchy.
Right, because if dealing with the waste is so toxic and expensive, the best solution isn't just burying it better. The ultimate solution sits at the very top of the hierarchy.
Source reduction.
Exactly. Just prevent the waste from existing in the first place.
Buy less stuff. Use less packaging. It's like preventative medicine for the planet. But, we still consume things. So we fall back on the 3 R's: reduce, reuse, recycle.
And we really need to emphasize reuse here because it brings up the concept of residence time.
Right. So if I buy like a really good winter coat and I wear it for 10 years or hand it down to my little brother, I am extending its residence time,
Yes, you're delaying its entry into the landfill.
which directly fights this whole throwaway society we've built.
Reusing is incredibly effective. Recycling, on the other hand, is way more complicated than people think. You need to know the difference between closed-loop and open-loop recycling.
Okay, break that down.
So closed-loop is the ideal scenario. It's when a product is recycled back into the exact same product.
Like an aluminum can turning into another aluminum can.
Exactly. And the reason that's the holy grail is because it perfectly closes the loop, meaning you completely eliminate the need to extract raw materials.
And for aluminum, that raw material is bauxite ore, right?
Yes. Mining bauxite causes massive habitat destruction and uses insane amount of electricity to smelt. Closed loop skips that entirely.
Another test prep pause. Look at Gage's Quizlet right now. Tie the word bauxite directly to aluminum in your brain. That will definitely be on the test.
For sure. Now, compare that to open loop recycling. This is when you take a product and turn it into a different, usually lower quality product.
Like taking plastic water bottles and spinning them into a fleece jacket.
Right. It keeps the plastic out of the landfill for a bit longer, but to make the next batch of water bottles, a company still has to go drill for virgin oil.
The loop is still open.
Exactly.
And honestly, modern recycling is even messier because of zero sort or single stream recycling. We just throw our cardboard, plastic, glass, and like half-eaten pizza boxes into one big blue bin.
Which is basically wish cycling.
Right. We toss it in and just hope the facility magically sorts it out. But doesn't this require huge amounts of energy and transportation and suffer from massive contamination?
Contamination is the fatal flaw of single stream. They did it to make recycling easier so more people would participate. But a single greasy pizza box can ruin an entire bale of clean paper.
Making the whole thing unrecyclable.
Yeah. And economically, it often becomes cheaper for cities to just send those contaminated blue bins straight to the landfill anyway.
Ugh, that's so depressing. Okay, so if complex plastics are a nightmare, what about organic waste? Like yard clippings and vegetable scraps. The solution there is composting, right?
Yes, but composting isn't just letting garbage sit there. It is a highly managed biological process. It's fundamentally aerobic decomposition.
Meaning it needs oxygen.
Exactly. Oxygen is the critical factor. You're basically farming decomposers, like bacteria and fungi.
Yeah.
And they need moisture, oxygen, and a specific carbon-to-nitrogen ratio.
Oh, the brown and green layers. I remember this. Brown materials are your carbon source. So like dried leaves, branches, cardboard.
Right, and they decompose very slowly.
And then green materials are your nitrogen source. Grass clippings, leftover strawberries, coffee grounds. They break down fast and get the pile really hot.
Exactly. So you mix them, you keep the pile turned so oxygen gets in, and you keep it moist.
Because if it dries out, the bacteria die.
Right. And when you maintain those aerobic conditions, the bacteria use oxygen to consume the organic matter, and they release water and carbon dioxide.
And what you're left with is humus, like really dark, nutrient-rich dirt.
Yes, it perfectly restores soil health.
Yes.
But, and this is crucial, there are strict rules about what goes in. Meat and dairy must never go in a compost pile.
Because rotting meat smells absolutely horrific and it brings in vermin. There's actually this wild historical detail in the sources. Back in the 1930s, towns literally just had open dumps.
Oh yeah, they just throw everything in a pit.
Including meat. It was such a big deal that national park dumps became actual tourist attractions. Families would go take pictures with swarms of black bears eating the garbage.
Which is a massive public health hazard. That's what forced the shift to modern engineered facilities. And that brings us to what happens if you don't compost.
Right. What if I put those same strawberry tops in a plastic trash bag and send it to a landfill?
Well, it gets buried under thousands of tons of compacted garbage. The oxygen is completely cut off.
So it goes from aerobic to anaerobic.
Exactly. And that shift completely changes the microbiology. The bacteria that survive without oxygen produce methane instead of carbon dioxide.
Methane, CH4. Which perfectly explains why, in the class audio, Mr. McConnell sounds like he has a deep personal vendetta against methane.
He really does.
It's pretty funny. But he's right to hate it because methane is 22 times worse for climate change than CO2.
Right. CO2 is a slow burn, but methane traps heat with terrifying efficiency. It's an aggressive spike to the climate system.
Okay, so a modern sanitary landfill is basically designed entirely around managing this toxic juice and explosive methane.
Yes, and you need to know the 5 structural components of a modern landfill for the test. Make sure you can visualize this.
Okay, let's build it from the bottom up. First, before any trash goes in, you lay down a thick clay or synthetic rubber liner.
That's your defensive shield to stop liquids from leaking into the earth.
Right. And then immediately on top of that liner is the leachate collection system.
Because as rainwater filters down through the trash, it absorbs battery acid, heavy metals, all that stuff. It creates leachate.
Which is basically toxic garbage kombucha.
That's a gross way to put it, but
Yeah.
if it breaches the liner, it poisons the groundwater. So they use pipes to pump it out for treatment.
Okay, that's 2. Third, because all that buried organic waste is making methane, you need a methane gas recovery system.
Right. They drive perforated pipes into the trash to suck out the explosive gas. And a lot of places actually burn that methane to generate electricity.
That's actually pretty smart. Okay, fourth, outside the actual trash pile, you have groundwater monitoring wells.
Just deep boreholes to constantly test the water and make sure the liner hasn't failed.
And finally, the fifth part, the clay cap. When the landfill is full, you seal the whole thing with clay and soil to keep rainwater out.
Right, and they usually plant grass on it. But building these facilities is a political nightmare because of NDBIY.
Not in my backyard. Because nobody wants a leaking, truck-heavy trash mountain next to their neighborhood.
Exactly. And the whole thing is funded by tipping fees. That's the price a city or company pays per ton to dump waste there.
But there's a weird catch, right? If the tipping fees get too high to pay for all this fancy engineering, people just start illegally dumping trash in forests to avoid paying.
Exactly. It's a perverse incentive.
So if landfills are these giant leaking methane bombs, why don't we just set it all on fire? Which brings us to incineration, or waste to energy.
Right.
And reading this, I realized an incinerator is essentially just an old school steam engine. But instead of coal, we're tossing in old couches to boil water and spin a turbine.
The physics are identical. The intense heat boils water, makes steam, makes electricity, and the huge benefit is volume reduction.
It shrinks the physical trash by up to 90%.
Yes, which saves a ton of landfill space.
But matter can't be destroyed, so you shrink the volume, but you concentrate the toxicity. Burning all that stuff creates fly ash.
Which is the stuff that floats up the chimney.
And it is incredibly toxic, full of heavy metals and dioxins. So even with scrubbers, you still have to take this super hazardous ash and bury it in a special landfill anyway.
Which perfectly introduces the whole concept of hazardous waste.
Okay, let's define that.
Hazardous waste is legally defined as any liquid, solid, gas, or sludge that is toxic, flammable, corrosive, or reactive enough to harm human health or ecosystems.
And getting rid of it is insanely expensive because you need specialized training and chemical reactions to neutralize it.
Right. So historically, companies would just secretly dump it.
Yeah.
That's why we have major legislation to handle it now. You need to know RCRA and CERCLA.
Oh, definitely. Look at Gage's Quizlet to get these acronyms locked in.
Yep.
RCRA was passed in 1976, the Resource Conservation and Recovery Act.
Think of RCRA as a preventative tracking system. It gives the EPA the power to track hazardous chemicals from the second they are made, all the way to their final disposal.
It's literal cradle-to-grave documentation.
Exactly. It ensures a barrel of toxic waste doesn't just mysteriously fall off a truck.
But what about all the toxic nightmares from before 1976? Or when a company illegally dumps chemicals and then goes bankrupt?
That is where CERCLA comes in, passed in 1980.
Better known as the Superfund Act.
Right. And the real-world example you need to know for this is Love Canal. A whole neighborhood and school were built right on top of an old chemical dump. It caused horrific birth defects.
It's so tragic. So CERCLA is reactive. It originally taxed chemical companies to build this massive trust fund.
Right. So when they find a toxic orphan site where no one can be held responsible, the EPA uses that Superfund money to clean it up.
And the absolute worst of those sites go on the National Priorities List, or the NPL.
Exactly.
But what if a site is gross and contaminated, but not quite apocalyptic enough for the Superfund list?
Those are called brownfields. They're old industrial sites or abandoned gas stations. They need environmental cleanup before they can be redeveloped, but it's usually handled by state and local governments.
With a little EPA help. Okay, so when these systems fail and pollutants get out, they eventually interact with us, which transitions us into human health and disease.
Right. We face three main types of health risks. Physical risks, like earthquakes, biological risks, which are diseases, and chemical risks.
And historically, humans mostly die from biological risks, infectious diseases caused by pathogens.
And we break those diseases down into two types. Chronic diseases, which happen slowly over a long time, like heart disease or cancer, and acute diseases, which hit rapidly, like Ebola.
And the way diseases spread is totally changing now. Because of globalization and urbanization, a virus can go from a remote area to an international airport in a day.
That's the difference between an epidemic, which is a localized outbreak, and a pandemic, which spreads across multiple continents.
Got it. Okay, for the test, there are some historically important diseases we need to run through.
First is the plague,
Right, caused by bacteria, and it's carried by fleas on rodents.
then malaria, caused by a protist parasite carried by mosquitoes, and you treat it with antimalarials.
And tuberculosis, or TB, it's a bacterial lung infection, and you treat it with antibiotics.
But epidemiologists are really worried about emergent infectious diseases.
These are the ones that are totally new or haven't been seen in like 20 years.
Right. Like HIV/AIDS, which is a virus, mad cow disease, which is actually caused by prions abnormally folded proteins.
Weird.
Yeah. Then there's Ebola, bird flu or H5N1, and West Nile virus.
But it's not just diseases, right? Our modern lifestyle, unhealthy diets, no exercise, smoking increases our risk factors. And on top of that, we have constant exposure to industrial chemicals.
Which brings us to toxicology, the study of chemicals that harm human health. There are 5 major types of chemical pollutants you have to know.
Let's do this. First up, neurotoxins. These specifically target the brain and nervous system, like the lead and mercury we talked about earlier.
Right, they slip past the blood-brain barrier and literally interrupt the electrical signals in your neurons.
Okay, second, carcinogens. These cause cancer. They mess with the cell's metabolism, so it grows out of control.
Asbestos is the classic example here. It causes a rare lung cancer called mesothelioma.
And closely related to that are mutagens, which directly mutate or damage your DNA.
Exactly. Fourth on the list are teratogens.
And these are just awful because they don't necessarily hurt the pregnant mother. They specifically target the fetus. They cross the placenta and cause severe birth defects.
The historical example is thalidomide. It was a drug given for morning sickness in the 50s, and it caused babies to be born with severely deformed limbs.
Just heartbreaking. Okay, what's the fifth one?
Endocrine disruptors. Your endocrine system uses hormones to regulate growth and reproduction. These chemicals are shaped so much like natural hormones that they act like a fake key in a lock.
So they bind to the receptors and just scramble the body's whole internal messaging system.
Right. Oh, and we should also mention allergens, which just cause abnormally strong immune responses in some people.
Okay, but how do these toxins, like mercury from a coal plant, actually get into us in high enough doses to hurt us? This brings up two terms that sound identical but are super different: bioaccumulation and biomagnification.
This is critical for the exam. Bioaccumulation happens inside one single organism over its entire life.
Okay, give me an example.
Imagine a single tuna swimming around. It absorbs tiny bits of methylmercury from the water. Mercury is fat-soluble, so the tuna can't excrete it.
So it just builds up in the tuna's muscle tissue year after year.
Exactly. That's bioaccumulation, the timeline of one fish. Biomagnification is the math across the whole food chain.
Oh, I get it. So plankton absorb a microscopic drop of mercury. Not a big deal. But a small fish eats 10,000 plankton.
So the dose magnifies.
And then a bigger fish eats 1,000 small fish. And the tuna eats hundreds of big fish. By the time I eat the tuna sushi, the mercury has magnified exponentially.
Right. Bioaccumulation is the storage. Biomagnification is the multiplication as energy moves up to trophic levels.
Test prep pause. Lock this difference in. Accumulation equals one organism. Magnification equals the whole food chain.
Make sure you have that written down. So looking at everything we've talked about today, from the daily avalanche of MSW to the chemistry of a compost pile, the methane from landfills,
The toxic fly ash, our CRA tracking, the biomagnification of neurotoxins in our food.
You can see how deeply human waste is tied into natural systems.
It's all connected, it's a massive web, but you guys now have the actual mechanics to understand it.
Exactly.
So give Gage's Quizlet flashcards one final review tonight. Visualize those 5 parts of the sanitary landfill. Remember, bauxite equals aluminum. And seriously, get some sleep. You are perfectly positioned to crush this APES test tomorrow.
And as you close your notes tonight, I want to leave you with one final thought about thermodynamics.
Okay, lay it on us.
In environmental science, we spend so much money and energy trying to figure out how to safely throw things away. But chemically speaking, there is no such place as away.
Right. Every atom has to be accounted for.
Exactly. When you throw something away, whether it goes up an incinerator smokestack or leaks out of a Superfund site or gets buried in a lined pit, it stays trapped inside the biosphere.
We're all in a closed loop.
We are. So just think about this. What would our economy look like if the concept of a trash can just didn't exist? What if every manufacturer was legally forced to physically consume 100% of the waste they created?
Man, that is a wild thought. Something to chew on while you're bubbling in those multiple choice answers. Good luck tomorrow, everyone. Catch you next time.